we must know that in the context of population variance estimation, because the population variance has a representation in terms of yi minus yj whole square, therefore, for estimation of the population variance, we need to divide yi minus yj whole square divided by pi sub ij. So, there we are concerned with positivity of all the second order inclusion probabilities pi ij and nothing more. On the other hand, for estimation of the variance of the Hornby-Thompson estimator, if we are in the framework of a fixed size design, we can refer to Yates-Grundy-Sen estimator of the variance estimate, and hence we can see that the moment pi ij is positive, that is essential, and we also need pi I times pi j greater than or equal to pi ij. So, these are the two things bothering us: strict positivity of all second order inclusion probabilities, and more than that pi I pi j greater than or equal to pi ij. So, in this module 9, we will be dwelling on some standard examples of sampling designs, and we will see how far these conditions are readily satisfied. So, as I said, pi ij is strictly positive for all pairs of units that must be satisfied in order that an unbiased variance estimator exists. But together with that there is an unbiased non-negative variance estimator that is ensured by the other condition, namely pi I pi j greater than or equal to pi ij for all pairs of units in the population. Also note that we are in the framework of a fixed size design, so that the same Yates-Grundy variance and variance estimate expressions are valid, and with that background we are talking about these sufficient conditions.
Sir, it seems though the above is just a sufficient condition, at least for sample size n equals 2, this must be necessary as well. Am I right?
Very much so. That is because the above sum for variance estimation reduces only to one term, namely the factor over pi I minus yj over pi j whole square multiplied by pi I pi j over pi ij minus 1. This is the only factor, and there is only one term. The square term involving the data is already non-negative, so you need the multiplier to be non-negative, and that amounts to pi I pi j greater than or equal to pi ij. Further to this, you must note that the condition pi ij strictly positive has to be enforced, and that also forces both pi I and pi j to be positive. You know, the inclusion and exclusion probability. Okay. I hope this is all clear to you. Also, for a very general sample size small n greater than 2, the above serves as a simple guiding principle for our choice of a sampling design. If the sample size is 5 or 6, there are so many terms in the expression for the variance estimate, we do not know which are positive and which are negative. On the whole, it may be positive, but we are not sure about it. So, to be on the safe side, we ask all pi I pi j to be greater than or equal to pi ij.
It is interesting to note that for simple random sampling without replacement, as also for stratified random sampling without replacement, we already know that these conditions hold. So no wonder we have non-negative variance estimates. In fact, it never occurred to us otherwise. Right, sir?
Yes, that's what happens. You don't really think over all these issues unless you come up with arbitrary sampling design. You face a situation of actual data analysis and find to your wonder, my God, I was not careful enough to make sure that all pi ij's are strictly positive. I was not careful enough to make sure that individual pairwise pi I times pi j is greater than or equal to pi ij. I was stupid enough not to think about all these things. I just thought let there be any sampling design under consideration. So you cannot really be that general. You need to have some basic conditions. More than that, you may check for yourself that the same inequalities, as you said, they hold also for PPS without replacement sampling scheme, even with a very general sample size small n. Good to take for small n equal to 2 first, but that is almost a trivial exercise.
Sir, in the context of PPS sampling, as you had mentioned, it is highly desirable that the pi's are increasing and the size measures p's. And that this is indeed so for PPS WR and PPS WOR sampling. However, for PPSW-OR sampling, you mentioned about an estimator entirely different from the Horvitz-Thompson estimator. Why so? It was based on computations of a sequence of conditionally unbiased estimators, T1, T2, and so on. Can't we use the HTE in this context as well? Sir, in the context of PPS sampling, as you had mentioned, it is highly desirable that the pi's are increasing and the size measures p's, and that this is indeed so for PPSWR and PPSWOR sampling. However, for PPSWOR sampling, you mentioned about an estimator entirely different from the Horvitz-Thompson estimator. Why so? It was based on computations of a sequence of conditionally unbiased estimators, T1, T2, and so on. Can't we use the HTE in this context as well?
Okay, that's a very good point, but let me go back and fix this notation. We are saying, yeah, the computation was based on a sequence of estimators, as you know, and we used the notation E1, E2, etc. So we better go back to those notations, okay, but we will fix it. Yeah, this is a very good question. Let us take it up. As you know, under or without replacement sampling, exact computations of pi I and pi ij's are extremely involved. That carries a discouraging sense in the use of the non-replacement estimator. Okay? For a very general sample size, if you are talking about without replacement sampling, it is extremely complicated. General expressions for pi I, pi ij, horrifying expressions. So we don't really find it any encouraging situation to go for computation of the Horvitz-Thompson estimator. In theory, we know what is involved in the expression for the HT variance and variance estimate. Those are straightforward, algebraically. But when it comes to computation, these are extremely complicated. That's why we look for some other type of estimators. Not only that, we know that this is an example of a non-cluster sampling design. It is known upfront that no unbiased estimator is unique. There are many unbiased estimators. So definitely beyond HT we can get one. And is there any simplicity in the computation of the estimator and its variance estimator? So we are guided by that principle. Okay? One idea is to use modified PPS, something while it uses the normed size measures, making the computations of pi I and pi ij very simple. That will be something that we will take up now. So the idea is that you keep PPS in your mind. Can you slightly modify it to get without replacement sample of size n? At the same time, can you simplify the computation of pi i's and pi ij's? So first point we have to understand that PPS without replacement sampling, computation of pi I and pi ij for a general sample size is extremely complicated. So either I take an escape route. What is the escape route? I think of another estimator. That is why we talked about Deshta's estimator, symmetrized Deshta's estimator. That was an escape route. Other route could be, even though I think of HT, can I simplify the computation of pi I and pi ij's? Not as such, but by modifying the PPS sampling. That is the spirit of this part. More than that, it makes pi I proportional to pi in the population as a whole and leads to not very complicated expressions for the pi ij's. So now we are thinking of modifying PPS without replacement scheme as such. Think of some modification of PPS, keeping without replacement in mind, keeping general sample size small n in mind, and adding the feature that computation of both pi I and pi ij are very simple. As a matter of fact, if pi I is proportional to pi, that is still desirable, and at the same time we don't want to have complicated expression for pi ij. Such sampling designs are aimed at achieving pi I proportional to pi. These are called pi PS sampling designs or sampling schemes. Pi means inclusion probability proportional to size sampling designs or sampling schemes. The interpretation being that the inclusion probability pi is proportional to the size measure. This idea of pi PS designs has been largely exploited, researched and documented. I described below one simplest such scheme due to Mizuno. You see the year 1952, long time back. Mizuno gave a scheme now known as Mizuno sampling scheme. The purpose was basically to modify the PPS without replacement sampling design to make it accessible to for a practical user. It says draw the first unit with pi equal to pi star. So draw the first unit with a different probability pi star. The remaining units with the same SRSW1. The first unit using some kind of modified probabilities P1 star, P2 star, Pn star. All the remaining units by without replacement sampling. See, altogether you get a sample of size little n, all distinct. Now you compute pi I for this scheme and make pi I equal to npi and thereby solve for pi star. Why pi I equal to npi? If pi I is proportional to pi and if summation pi I equal to small n, that is a result involving the inclusion probability and the sample size because you are referring to a fixed sample size. Therefore, pi I equal to n times pi. So equate pi I to npi, and from this sampling design, you know that pi I is a function of pi star. So from there you solve for pi star as a function of pi, and here is the result. So you can find out for yourself by direct computation that pi I is given by this expression, equate that to npi, and then get the expression for pi star. These pi star, they are to be regarded as the size measures for the initial catch, for picking up the first unit. After that, of course, you are guided by simple random sampling without replacement. So in order that you can use the pi stars as the inclusion probability, of the units in the first stage, you have to have pi star greater than or equal to 0, and they have to add up to 1. That they add up to 1 is trivial because of the fact that summation pi equal to 1, so that one can very easily verify. So for pi star greater than or equal to 0, you need this condition. So what is the idea? We are given the original size measures P1, P2, P capital N. You know the sample size small n, you know the population size capital N. Verify this condition pi greater than or equal to small n minus 1 over small n into capital N minus 1. If this condition is satisfied, you are ready to apply mid-zero sampling scheme, a modified version of PPS. Still you are using a sample without replacement sample of size n. Once these conditions are satisfied, you may use the PIPS sampling scheme. And for such a scheme, it is a routine exercise to work out pi ij. You can see that pi ij is positive, and you can verify readily that pi I times pi j greater than or equal to pi ij for all disjoint units in the population. This sampling scheme has been generalized in different directions. Many other PIPS sampling schemes have been suggested. Let me go back to the basic question again in respect of choice of a fixed size sampling design. What about variance estimation? That means unbiased estimation of sigma square. Do we still need pi ij positive for all pairs of units in the population? What about non-negative variance estimation? What are the conditions on the pi ij's vis-a-vis pi I and pi? It is not a difficult exercise, and I am sure you can elaborate on this. So these are the things coming up. I already mentioned in so many terms the difference between estimation of population variance, be it sigma square or S square, and estimation of the variance of the Hurwitz-Thompson estimator. That is also variance, but this is the population variance, and that is the variance of the Hurwitz-Thompson estimator. Both are quadratic, both need estimation, unbiased estimation, both need the condition pi ij strictly positive. For variance estimation, sigma square estimation, pi ij positive is good enough. For estimation of the variance of the Hurwitz-Thompson estimator, there you need pi I, pi j greater than or equal to pi ij. That extra condition also creeps in. Of course, that is a sufficient condition, but that helps. On the other hand, for unbiased variance estimation, pi ij positive, that immediately ensures that you have a non-negative variance estimate. I think I will stop now. In module 9, we continued to dwell on various aspects of estimation of the population total or the population mean and estimation of the population variance or variance of the Hurwitz-Thompson estimator of the population total. In all these cases, we have to be guided by right choice of the designs, whether it is a general sampling design or a fixed size sampling design. The condition pi ij strictly positive for all pairs of units, that is an integral part regarding the choice of the sampling design, failing which it is impossible to unbiasedly estimate any quadratic form, which like population variance or the variance of the Hurwitz-Thompson estimator. On the other hand, the condition pi I, pi j greater than or equal to pi ij, that is a welcome condition, because basically it is a condition on the choice of the sampling design. So, we can always try to make sure that this condition is also satisfied for all pairs of units, and there is a big advantage in doing so, at least for fixed size sampling designs, by referring to Shane-Yates-Grundy variance expression formula and that of the estimate of the variance as given by Shane-Yates-Grundy. We can immediately say that, oh, okay, whatever be the data we are relieved, we are not going to face the problem of negative variance estimation. That part immediately can be taken care of the moment we know pi I pi j greater than or equal to pi I j for all possible units in the population. It is a good aspect to know the precaution to be taken in our making choice of an appropriate sampling design. Fortunately for us, the standard sampling designs, they do satisfy this condition, but then there is a danger in using the PPS without replacement sampling. The expressions for pi I and pi ij's are so complicated that really it sends a discouraging note. That is why long time back Mizuno, in as early as 1952, he suggested a scheme. That scheme has two purposes. One is making pi I proportional to pi. It is a modification of PPS without replacement sampling for a general sample size. It has got dual purpose. Number one, pi I proportional to pi, and as a matter of fact pi I equal to n times pi, small n times pi for every I. And secondly, the expression for pi ij is conveniently simple, and moreover pi I pi j greater than or equal to pi ij. This condition is also satisfied. With that in mind, Mizuno suggested a scheme known as Mizuno scheme that we have elaborated in this module, and then we took up some other issues. Now, let us go forward to take up some exercises and MCQs. It seems I am quite excited about these topics. The fact is that it has been my business to talk about these things, to think about these things, to work on these some of these topics for so many years. I ended up writing a textbook in 1991 with Professor Hidayat. That is a Wiley publication. But anyway, that is referred to in some places. Anyway, let us take up some theoretical questions. Question number 1. It is much easier to visualize the problem of non-negative unbiased estimation of a finite population variance than that of variance of the Horbes-Thompson estimator. While HT Horbes-Thompson estimator seeks to provide an unbiased estimate of the population mean. Elaborate on this phenomenon. It is a good problem. So, what is the point of distinction between estimation of population variance and estimation of the variance of the Horbes-Thompson estimator? Point of similarity, they both are quadratic in nature. Point of distinction, they too have different expressions. In both of them require pi I is strictly positive, whereas for population variance estimation, pi I is strictly positive is good enough to provide non-negative unbiased estimate. For the other, it is desirable that pi I pi j greater than or equal to pi I j, that condition is also imposed. That condition is also satisfied by our choice of the sampling design. So, this is something that one can really write one can write a technical essay on this aspect of the two variance estimation problems. Problem number 2, provide 3 examples of without replacement sampling designs providing non-negative unbiased estimators of a finite population variance. In each case, examine the status of the design for non-negative unbiased estimation of variance of the Horbes-Thompson estimator. Very good problem, because we know for estimation of finite population variance, all we need is pi I j strictly positive. So, once we make a selection of a sampling design only following this principle of non-negative, principle of positive inclusion probability for all pairs, something may go wrong regarding the inequality pi I pi j greater than or equal to pi I j. So, it is interesting to see how far the second condition is also satisfied by your choice of sampling designs, and I would expect that you will come up with intelligent examples where pi I j positive is of course absolutely guaranteed, but then it is a tricky situation. The other condition is not necessarily guaranteed, and we end up with negative variance estimation. That is the tricky part here. Please read the next one.
A without replacement NN sampling design provides unbiased estimator for the variance of the Horvitz-Thompson estimator. Does it necessarily provide non-negative unbiased estimator of population variance capital S squared? Justify your answer.
It's again a good but trivial but interesting question. It says, if you know that one without replacement sampling design provides unbiased estimator of the variance of the Horvitz-Thompson estimator, immediately you know all pi ij's are positive, because pi ij has to be positive for estimation of the variance of the Horvitz-Thompson estimator, because variance involves the square term as well as the quadratic cross product term, and for cross product term you need pi ij positive. So that is implied immediately in the first part of the question. And once pi ij is positive, you know you can estimate population variance by using non-negative unbiased estimator simply by dividing by pi ij. This is the kind of thing we have been talking about again and again. So it is a tricky problem. It's a tricky problem, but very easy solution. What is the next problem?
Suggest 3 examples of without replacement capital N small n sampling designs such that pi ts is less than or equals pi t pi s for all pairs of units belonging to a chosen sample of size n in each example. Comment on your examples.
This is a good problem again. I would suggest take small n equal to 3. So you have to suggest a sampling design. There are 3 examples, but let me talk about one example. You have to suggest an example of a sampling design where, for example, a sample of size 1, 2, 3 is already there. And then you show how you can manipulate on the example of the sampling design so that pi 1, 2 is less than equal to pi 1 times pi 2, pi 1, 3 less than equal to pi 1 times pi 3, pi 2, 3 less than equal to pi 2 times pi 3. So make sure that you can have this thing for all pairs of units belonging to a chosen sample. They are talking about belonging to a chosen sample of size n in each example. So you choose a sample, as I said, suppose the sample is 1, 2, 3, you make sure that this condition is satisfied for the sample 1, 2, 3. This is an interesting comment on your examples, because if you are satisfied with this condition for the chosen sample of size n, does it really tell you that you have solved the problem of non-negative variance estimation? That's a good problem. Okay, think about it. Is there anything else or no? Okay. So thanks for your attention. I think that's it.
It is required to provide non-negative unbiased estimator of a finite population variance based on a sample selected according to a chosen without replacement sampling design. It is necessary and sufficient that 0 less than pi ts less than or equals pi t times pi s for all pairs of units t unequal to s in the chosen sample of size n. True, false, true provided n equals 2, or true provided n equals 2 and the above inequality holds for all pairs of units in a population.
So you have to be a bit careful in reading the question. So the first part is okay. You are required to provide a non-negative unbiased estimate of the population variance. The moment it says population variance, you know necessary sufficient condition is pi I is strictly positive for all I and j. That means pi t is strictly positive for all t and s. You don't need to relate it to pi t times pi s. No, that's not needed. So that's the answer we know. So you don't really have to worry about pi t times pi s and that inequality, and that you don't have to worry about small n equal to 2, nothing like that. But it says for all pairs of units in the chosen sample of size n. In a chosen sample of size n, if I find that this condition is satisfied, does it resolve the problem? That's why you have to think a little bit, okay? What is the next one?
It is much easier to visualize the problem of non-negative unbiased estimation of a finite population variance, capital S squared, than that of variance of the Horvitz-Thompson estimator, where the Horvitz-Thompson estimator seeks to provide an estimator of the population mean.
Okay.
This is true if the adopted WOR sampling design is, in effect, a simple random sampling without replacement sampling design, in effect, a PPSWOR sampling design with small n equals 2, in effect, a PPSWOR sampling design with small n more than 2.
So they are giving examples of 3 sampling designs. One is SRSWR, arbitrary size, other is PPSWR, sample size 2, other is general PPSWR. And they are asking how do you assess the two questions? One is estimation of population variance, other is estimation of variance of the horizontal estimator. What is the difference in the difficulty level of the two problems? That is the question here, okay? Next one.
A without replacement sampling design has been so chosen that 0 less than pi ts less than equals pi t times pi s for all pairs of units in a chosen sample. This leads to non-negative population variance, capital S squared, estimation, is also to non-negative estimation of the variance of the Horvitz-Thompson estimator. Both statements are generally true, both are generally false, only one of the statements is generally true, none of the above is true.
Yeah, it's a very tricky question. These are none of these questions is really difficult, but a bit tricky, and you have to pay attention to the wording that is given here. Everywhere they are saying this condition, etc., for all pairs of units in the chosen sample. They are not saying anything beyond if something else had been chosen. That's the point here we have to note. Okay, you must make sure for the chosen sample they are saying that this has happened, so you can do this computation, that computation, but they are not telling what would have happened if the sample was a different sample. In the still captured by the sampling design, it was a different sample. Then what would have happened to these conditions? So that is the tricky part here. Okay, you have to think carefully. Good.